Chapter 7. What are standards? One has to go rather slowly on fixing standards, for it is considerably easier to fix a wrong standard than a right one. There is the standardizing which marks inertia, and the standardizing which marks progress. Therein lies the danger in loosely talking about standardization. There are 2 points of view, the producers and the consumers. Suppose, for instance, a committee or a department of the government examined each section of industry to discover how many styles and varieties of the same thing were being produced, and then eliminated what they believed to be useless duplication and set up what might be called standards. Would the public benefit? Not in the least, excepting in wartime when the whole nation has to be considered as a productive unit. In the first place, no body of men could possibly have the knowledge to set up standards, for that knowledge must come from the inside of each manufacturing unit, and not at all from the outside. In the second place, presuming that they did have the knowledge, then those standards, although perhaps affecting a transient economy, would in the end bar progress, because manufacturers would be satisfied to make to the standards, instead of making to the public, and human ingenuity would be dulled instead of sharpened. Some standards, of course, are necessary. An inch must always be an inch. When we buy by weight or by measurement, we ought to know what we are buying. Every number 9 shoe in the country ought to be of the same length. A quart ought to be a quart, and a pound ought to be a pound. To that extent, standardization is a convenience and a help to progress, and likewise with description. A certain grade of cement ought always to be of the same grade, so as to relieve the careful buyer from the necessity of testing. All wool ought to be all wool. Silk ought to be silk. The small buyer, who has no facilities for testing, should be able to rely on a published description of any article. All this, to repeat, is a matter of convenience, and also it prevents the unfair competition, which permits an inferior article and a superior article both to be sold under exactly the same description. But when we come to styles, we have an entirely different matter. Those who are unacquainted with the processes and the problems of industry are given to picturing a standardized world in which we should all live in the same sort of houses, wear the same sort of clothing, eat the same sort of food, and all think and act in the same way. That would be a prison world, and such a world is not possible until all the human beings in the world stop thinking. It is hard to imagine how such a world would get along, for with everyone thinking or not thinking in exactly the same way, leadership would vanish. The eventuality of industry is not a standardized automatic world in which people will not need brains. The eventuality is a world in which people will have a chance to use their brains, for they will not be occupied from early morning until late at night with the business of gaining a livelihood. The true end of industry is not the bringing of people into one mold. It is not the elevating of the working man to a false position of supremacy. Industry exists to serve the public, of which the working man is a part. The true end of industry is to liberate mind and body from the drudgery of existence by filling the world with well-made, low-priced products. How far these products may be standardized is a question not for the state, but for the individual manufacturer. The strongest objection to large numbers of styles and designs is that they are incompatible with economical production by any one concern. But when concerns specialize, each on its own design, economy and variety are both attainable, and both are necessary. Standardization, in its true sense, is the union of all the best points of commodities with all the best points of production, to the end that the best commodity may be produced in sufficient quantity and at the least cost to the consumer. To standardize a method is to choose out of many methods the best one and use it. Standardization means nothing unless it means standardizing upward. What is the best way to do a thing? It is the sum of all the good ways we have discovered up to the present. It therefore becomes the standard. To decree that today's standard shall be tomorrow's is to exceed our power and authority. Such a decree cannot stand. We see all around us yesterday's standards, but no one mistakes them for today's. Today's best, which superseded yesterday's, will be superseded by tomorrow's best. That is a fact which theorists overlook. They assume that a standard is a steel mold, by which it is expected to shape and confine all effort for an indefinite time. If that were possible, we should today be using the standards of 100 years ago, for certainly there was then no lack of resistance to adopting what goes to make up the present standards. Industry today, under the impulse of engineering ability and engineering conscience, is rapidly improving the standards. Today's standardization, instead of being a barricade against improvement, is the necessary foundation on which tomorrow's improvement will be based. If you think of standardization as the best that you know today, but which is to be improved tomorrow, you get somewhere. But if you think of standards as confining, then progress stops. We believe, as was fully developed in my life and work, that no factory is large enough to make two kinds of products. Our organization is not large enough to make two kinds of motor cars under the same roof. Several years ago, we bought the plant of the Lincoln Motor Car Company, more for personal reasons than because we wanted it. Our Model T, the Ford, is our principal business, and we have made it a commodity. We have no desire to make a commodity out of the Lincoln. Its standards are no higher than those of Model T, but they are different. Both cars are what might be called standardized, in that every improvement has to be so arranged that it will fit on an existing car without machine work. Of course, all parts are interchangeable, which is one of the advantages of machine work over hand work, which is not generally appreciated. It is always possible to devise a machine which will do better and more accurate work than can be done by hand. But the point is that though the one company makes these two types of cars, they are not made under one roof, and they are made from different motives. The Model T is low-priced and serviceable. The man who makes it can buy it. The Lincoln effort is not in the direction of prices at all, and the man who makes it cannot buy it. It is not a luxury car in the sense that it performs no service. It gives supreme service, but it is not a commodity. There must be grades of service, just as there are grades of human beings. One man's effort will bring him a return sufficient to buy one kind of article, while another man's effort will bring him a return sufficient to buy something higher in price. This is not violating the principle of the wage motive. It is extending that principle through all grades of service. We must level upward and not downward, and keeping that principle will prevent standardization from ever becoming a menace. It is essential to economical manufacturing that parts be interchangeable. We do not make Ford cars in any one place. We turn out only a few completed cars in Detroit, and those only for the local market. We make parts, and the cars are assembled where they are to be used. And this involves an accuracy in manufacturing beyond anything thought of in the old days. Unless parts fit accurately, the resulting assembly will have lost motion, and much of the economy of design will be lost. That took us into the necessity for absolute precision in manufacturing, a precision extending, in some cases, to a 10,000th of an inch. Under ordinary circumstances, gauges cannot be kept so accurate. Of course, only in exceptional cases do we work so accurately, but in many, perhaps in most of our tolerances, we work to 1,000th of an inch. And to gain this accuracy, we sought out the one man in the world who had made a business of absolute accuracy, and brought him into the organization, Carl E. Johansson. As a foreman in the Swedish government arsenal at Eskilstuna, he conceived the idea of combining solid master gauges used in the production of accurately finished rifle parts, so that a greater number of dimensions could be obtained from a small number of blocks. The first set was produced in 1897. Today, Johansson gauge blocks are recognized throughout the world as the most accurate precision instruments known. We purchased the American manufacturing rights for Johansson gauges, as well as the plant at Poughkeepsie, New York. More important still, Mr. Johansson joined the organization as a member of our engineering staff to develop further his precision instruments. Johansson combination gauge blocks are rectangular pieces of tool steel, hardened, ground, and lapped. Their surfaces are absolutely flat and parallel, one of the most remarkable achievements in mechanics, as the difficulty in making one steel surface truly parallel to another is a universally recognized problem. Professor J. Helsley, head of the Department of Mathematics at the University of Copenhagen, states that the surfaces of these blocks more nearly approach the perfect theoretical plane than any other produced by the hand of man. These surfaces possess extraordinary qualities when rubbed across the palm of the hand and brought in contact with one another, sticking together with a force equivalent to 33 atmospheres. Scientists have offered various theories in explanation of this phenomenon: atmospheric pressure, molecular attraction, and the presence of a very minute liquid film on the contacting surfaces. Possibly it is a combination of all three. Two blocks wiped across the skin and pressed or wrung together with a slight sliding movement have resisted a direct pull of 210 pounds, which proves that there is something besides air pressure that makes them stick. Some of the sets differ in steps of 1/10,000th of an inch, while others differ by as low as 1/100,000th of an inch. A 10,000th is about the lowest limit of accuracy in fine tool-making, but this seems almost crude when measured with Johansson gauges. The ultimate, however, has been reached in a set which differs in steps of 1/1,000,000th of an inch. This is so delicate that even the heat of the user's body several feet away influences the results. It is the only set in the world. While we have a monopoly on these gauges, our first move after acquiring the American rights was to improve the manufacturing processes to increase the output and decrease the prices, so that these gauges would be within the reach of every machine shop and tool maker, which incidentally proves that there is nothing incompatible between quality and mass production. At the Highland Park, we have 25,000 machines, and at Fordson, 10,000 more. Scattered throughout our various plants, we probably have an additional 10,000. From time to time, we are called on to fit out new branches in various parts of the country and of the world, and also to have at hand spare parts for these machines. That brought us into an important division of standardization. An operation in our plant at Barcelona has to be carried through exactly as in Detroit. The benefit of our experience cannot be thrown away. A man on the assembly line at Detroit ought to be able to step into the assembly line at Oklahoma City or Sao Paulo, Brazil. We use single-purpose machinery. That is, a machine is called on to do only one operation, although in the case of an automatic machine, that operation may consist of several parts. The tendency is always for tool designers to make each machine from the ground up, without reference to any other machine. About 90% of our equipment is standard, and the conversion into a single-purpose machine is a matter of detail. For instance, one operation calls for the piercing of a steel billet with a hole 7/8 of an inch in diameter. Formerly this had been done by drilling, which was slow and costly, using many men and 30 drill presses, and wasting a lot of material. Then we substitute a standard disc-piercing mill, for which our men designed a new set of tools, and made it do an entirely different job from the one for which it was originally intended. It is estimated that more than 500 miles of boring was done before this time and labor-saving machine was developed. We have 800 special machines designed to meet our own conditions of work. The major classifications of the standard machines are under 250 different headings, each of which is divided and subdivided into types and varieties until the list runs into the thousands. Under the headings like lathes, millers, grinders, presses, saws, drills, etc., come lists of hundreds of different varieties, each of which is different in design and size. Yet, with production standing at more than 8,000 cars a day, there is less money tied up in perishable tools than when the company's productive limit was 3,000 cars a day. The reason for this is standardization. These tool standards are the result of 20 years' work. Today, the system has been developed to such a stage that our manufacturing tools are as easily obtained as commercial hardware. This also applies to the tools and equipment used in making productive machinery. Gears, keys, shafting, levers, pedals, and other elements that make up a machine are all standardized. And out of various combinations of these standardized parts, even highly specialized machinery is built. Some of the most intricate designs have been built with no other special work than the frame casting. The glass grinding machinery illustrates this. Here the disc driving mechanism consists of the standard Wurman gear and the disc elevating mechanism of the standard ring gear pinion, axle shaft, and steering wheel. This simplification of the equipment problem is the basis on which the manufacturing program rests. This system is carried out in every branch and manufacturing unit, not only in equipment, but in shop methods. The conveyors used at the various branches and the chains used in their construction are all standard. All stock comes in standard sizes. Blueprints are made in a certain standard form, with the various information always listed in the same location on the sheet, so that no time need be wasted in hunting for it. A series of books entitled Ford Tool Standards contains all the necessary data and gives the complete story of our standard practice with all its ramifications down to the last detail. These books have saved thousands of dollars in the training of new men, but their real importance cannot be estimated, for they are primarily responsible in keeping the work uniform throughout the entire organization. The advantages of this system of standardization of machine tools and equipment are numerous. The machine tool problem is reduced to a simple hardware affair and is hardly more expensive. Immense savings are possible in the construction of standard and special machinery, and if a design proves unsatisfactory, its major parts may be salvaged. The equipping of branches and manufacturing units becomes greatly simplified, and emergencies can be met without special effort. Furthermore, the maintenance and repair of machinery and tools is made simpler and easier. How much a year this saves for us can only be guessed at. The advantages of standardization are apparent in production. The disadvantage is the expense incurred when changing from the standard. But the cost of changes is usually more than compensated by the improvements which a change gives opportunity to make. We have made many improvements in design and materials, and of course in manufacturing methods. But the benefit of every improvement has been passed on to the public. The design has been as good-looking as we knew how to make it, considering that each part had to be made in the light of these three principles, given in the order of their importance. 1. Strength and lightness. 2. Economy in manufacture. 3. Appearance. It may be asked, is it not better to sacrifice the artistic to the utilitarian than the utilitarian to the artistic? What, for instance, would be the use of a teapot that would not pour because of the ornate design of its spout? Of what use would be a spade which cut one's hands because the handle was richly carved? As soon as the decoration on an object of utility interferes with its functioning, it ceases to be an object of art and had better be discarded as a nuisance. It has been said that trade and industry are fatal to art, but that is not true. When art is divorced from utility, something is wrong. Industry and art are not incompatible, but sound judgment is necessary in preserving the true balance between them. An automobile is a modern product and has to be designed not to represent something which it is not, but to do the work for which it was intended. Last year we made certain changes to the end of turning out somewhat better cars. The engine we did not touch, that is, the heart of the car. In all, 81 changes, major and minor, were involved. None of these changes was made lightly. The new designs were thoroughly tried out all over the country in actual service for many months. After we had decided to make the changes, the next step was to plan how it could be done. We set a date to begin changing over. The planning department had to calculate on just the amount of material which would keep production going at full speed until that date, and then permit production to stop without having any material left over. It had to make the same calculations for our 32 associated plants and for the 42 branches. In the meantime, hundreds of drawings had to be made by the engineers for the building of the new dies and tools. We arranged to make this change without a wholesale shutdown. We staggered the process, changing one department at a time, so that by the time the last change was made, production had caught up to the last department involved. All of this sounds simple enough, but here is what it meant to make only 81 changes. We had to design 4,759 punch and dies, and 4,243 jigs and fixtures. We had to build 5,622 punch and dies, and 6,990 jigs and fixtures. The labor cost of this amounted to $5,682,387, while the material ran to $1,395,596. Installing the new enamel ovens at 13 branches cost $371,000, and changing the equipment in 29 branches cost $145,650. That is to say, these changes cost us upward of $8 million, not estimating time lost from production.